Okay, so now problem 3. So problem 3 says, that asks us to calculate the pH for a 0.1 molar solution of either part A, which is HNO3, nitric acid, or HNO2, which is nitrous acid. So first, let's look at part A, which would be nitric acid. And we look at first the strength of the acid or the base or the salt. In this case, it's a strong acid. So that means it fully dissociates, just like what we've talked about previously in problems 1 and 2. So then, if we're figuring out the pH, it's super straightforward. We take our equation for our acid. It goes completely to H plus NO3 minus, nitrate ion. And if we put our ice table together, we know that we start with 0.1 molar, and we start with no acid or H plus or anion. Our change is it's fully dissociated, so that means that this is minus 0.1. This becomes plus 0.1, and this becomes plus 0.1. Our equilibrium concentrations are, there's no more acid, there is 0.1 molar concentration of H plus ions, and 0.1 molar concentration of nitrate ions. So because we're looking for pH, we very simply just say pH is equal to the negative log of our concentration of H plus. So that is negative log of 0.1 molar, which is then equal to 1. So this answer is still consistent with what we talked about in class the other day. We just show that in order to calculate pH, we can go directly to putting in the concentration as 0.1 and solve, and we have our concentration to be 1. Part B is a little bit different. So for part B, now we have a weak acid, which means that we get partial dissociation. So let's set up our ice table. Well, first our reaction is HNO2, double arrows because it's partially dissociating, into H plus and NO2 minus, right? So initially, we start with still 0.1 molar, and we still don't have any protons and we don't have any ions yet. The change, we assume that it's only partially dissociated, so only a piece of this is going to convert to H plus and NO2, and we signify that by X. And then we add this X on either side. And then our equilibrium concentration is then equal to 0.1 minus X, X, and X. And X represents our concentration of protons. Now we need to apply our Ka equation to figure out, to then eventually solve for X. We have information saying that the Ka is 4.5 times 10 to the minus 5. So let's put that in. Well, let's first say Ka is equal to H plus times NO2 minus over H NO2, right? So when we put in our values, we say that 4.5 times 10 to the minus 5 is equal to x times x over 0.1 minus x. And so now we can then solve for our for x to then figure out our concentration. Now I'm going to apply an approximation. The next video is going to explain exactly the breakdown of that approximation and some other information that we're going to use to do some further solving. But first, we're going to assume an approximation. Oh, I tried to combine too many words. Assume approximation. And we're going to assume that this x that comes off, this tiny little part that comes off, is going to be a whole lot smaller than the 0.1 molar concentration. If we assume that to be true, and like I said, the next slide will explain why we can make that approximation. I gave you an example or an answer for that in class. I'm going to expound on that. That hopefully will be straightforward. Okay, so since we make this approximation, we can then say 4.5 times 10 to the minus 5 is equal to, this is going to go to 0 because we're assuming that this is going to be very small. And so this is going to go away. I shouldn't say it goes to 0. Let's just say we're crossing it out because we're saying that's really, really small. And then this is equal to x times x over 0.1. So now we can solve for x. And we're not using the quadratic formula. And we find out that our x, once I find my paper, where is my paper? Right. Our x is equal to 0.00671. And the pH is equal to 2.17. And that's because we take, in order to get the pH, that's equal to the negative log of this concentration of x, because this is equal to H plus 0.00671. We calculated from here by solving for our x to be equal to 0.00671. That is x, which is here, and x is equal to the concentration of H plus ions. So we then take the concentration of H plus ions, which is x, as shown from our ice table. We put it in here, the negative log of this, and then we get our pH to be 2.17. So, cool. We got our first answer. Now, also what's not in here is the next little part that asks for the percent dissociation. So, we are going to calculate that. I'm going to erase a little bit of this so that we can go ahead and calculate it. In fact, I'll erase all this. So the percent dissociation, also known as the percent ionization, or the percent of hydrolysis, that's it, hydrolyzed, these words, okay, is equal to the concentration of H plus over the initial concentration of our weak acid times 100. I shouldn't have erased that ice table. But what that means is basically this is our X, whatever reacted in the reaction. All right, let me put my ice table back. So H NO2 goes to H plus NO2 minus. Initially we start with 0.1, we have nothing, and then we have minus X plus X and plus X, and then we have our equilibrium, that's 0.1 minus X, X and X. So when we figure out the percent dissociation, we take the concentration of H plus that was ionized or dissociated, as shown in the ice table, because this is our equilibrium concentration, and we take the initial concentration of the acid that we first started with. So we're basically trying to figure out what reacted, what was consumed in the reaction, and that's the percent dissociation. And so we put these values in. So H plus is equal to 0.00671, and that's divided by our initial concentration of acid, which is 0.1 times 100. And we calculate our percent dissociation to be 6.71% dissociation. So then this is correct.